Today we are honored to have Dr. Daniel Haskel here from Argonne National Lab. Daniel is a senior scientist, senior scientist, a physicist? Senior scientist. Pretty high ranked in the national lab. And Daniel graduated from University of Washington in 1998. And after that, and he moved to Argonne National Lab and has been there since then. And he ran the magnetic material group as a group leader, and has won many recognitions and awards, including a fellow of American Physical Society, and many awards that I won't read line by line. He is gonna talk about X-rays and the magnetism in today's colloquium, and then tomorrow he's going to give a more focused talk on quantum spin liquid, I guess, using X-ray, probably mostly XMCD, to probe the quantum spin liquid state at the condensed matter physics seminar tomorrow at 11 a.m. Right? Yeah, let's welcome Daniel.
All right, thank you all for coming. I want to start by thanking, can people in the back hear me? Yes, okay. I want to start by thanking Wenli for the invitation. When she contacted me, she said you should come to take a break from the Chicago weather, and it's still true. I know you guys complain it's cold here, but we have a 30-degree differential today, so it's very nice to be here. I also really enjoyed the conversations I had with a bunch of faculty today, so thank you to those that took the time to show me your research. Pretty exciting stuff going on here. So today the plan that I had for this talk was to tell you a little bit about the interaction of X-rays with matter, and in particular where the sensitivity to magnetism comes from. That's not a trivial thing. I will try to highlight where the uniqueness of these techniques is, how do they augment and complement other probes of magnetization, and I have a few examples throughout the talk, and hopefully we have enough time for questions. So X-rays are not the first thing that comes to your mind when you think about probably magnetic structures. You're thinking about imaging with X-rays, you're thinking about diffraction with X-rays, but magnetism is not really the thing that you think about when you think about X-rays. That's a picture of Röntgen's wife's hand. Apparently she was pretty scared about this image. He won the Nobel Prize more than 100 years ago. Lowy figured out diffraction, and then the Bragg father and son came up with Bragg's law. The son was 25 years old when he got the Nobel Prize. Still a record, nobody else got it below 30. There's a bunch 30 plus. So neutrons are the thing that comes to mind when you think about probably magnetic structures, because neutrons have a spin half, and you can polarize them, and the spin of the neutrons directly interacts with the spin of the electrons. So you get very strong magnetic scattering from the electron spin, and you can also probe the lattice structure because the neutron interacts with the nuclei of the atoms. So whether you have antiferromagnetic order, where the periodicity of the magnetic structure is not the same as the lattice periodicity, or whether you have ferromagnetic order where the periodicity of the magnetic structure is the same as that of the lattice. In that case, the magnetic scattering is on top of the lattice or nuclear scattering. And even then, you can see it very clearly in neutrons because the magnetic and the nuclear scattering cross-sections are similar. So Schul won the Nobel Prize for showing that neutrons can be used to probe magnetic structures. And when you think about X-rays, X-rays have orthogonal electric and magnetic fields, oscillate, it's an electromagnetic wave. and then these fields interact with the electron's charge on the spin. So naively, you would think that the electric field of the X-rays will couple to the charge, and the magnetic field will couple to the spin. And that is more or less the case. But what we'll see today is that the sensitivity to magnetization comes predominantly, and it's pronounced by coupling to the electric field, not the magnetic field. And that happens at resonances when you tune the X-ray energy to near absorption edges, electronic transitions in an atom. So that's what leads to the strongest spin sensitivity. And I want to walk you through some of these fundamentals in a very high level. So we start away from resonances, and everybody I think is familiar with X-ray scattering or X-ray diffraction. The electromagnetic wave comes in, the electric field oscillates, and it causes the electrons in the atoms to oscillate along the same direction, and that acceleration causes dipole radiation. And much like an antenna, you have a current that goes back and forth. The charges are accelerated, and you emit electromagnetic radiation at the same wavelength that the incoming radiation here. So accelerated charges emit radiation, and that's dipole radiation. The polarization doesn't rotate, it keeps its orientation. And this scattering is basically proportional to the number of electrons you have in the atom. And the relevant quantity here is the classical electron radius, R0. And if you have, for example, an atom of neodymium with 60 electrons, the scattering power is sort of like 60 R0. Now, when you get near resonances, things change. And you know we have X-ray absorption near resonances, and here we have an absorption edge near the neodymium L2 resonance, which is a 2p1/2 core level excitation. So obviously these X-rays are getting absorbed, so less X-rays are getting scattered, and there is a modification or an addition to the scattering cross-section, which is captured by these complex scattering factors. You are exciting an electron into an empty state above the Fermi level, and then the electron comes back. So it's a virtual intermediate state, a second order process, and when the electron comes back and fills the hole, the radiation is emitted again with the same X-ray energy. So it's a second order process. The polarization is the same as the non-resonant one, and it's rather large. So it's about, if you look at this step here, it goes from about 10 to 12 because the 2p1/2 core has 2 electrons. But when you put that atom in a solid, this valence electron or valence empty state is not just one atomic orbital, but it's a band in the solid, and this cross-section is modified, so it goes much higher. So instead of 2, it's actually about 7. So it's 10% of the non-resonant part. But there is no sensitivity to the magnetism here. This is just sensitive to the empty density of states, or the number of holes you have in the orbital in this intermediate virtual state. Now, if you have spin in the valence electrons, so you have a magnetic atom, you're exciting an electron from a core level that also has a spin. So that spin of the core electron, when it's excited, interacts with the spin of the electrons in the valence orbital, or the outer orbitals, or the valence band. And you get sensitivity to the size and the direction of the moment. And again, this is a second order process. The electron comes back, fills the hole, and you get radiation out. And you see that the polarization now is different. Now it's sort of rotated, but this magnetic scattering amplitude captures the strength of this effect, and the direction of the magnetic moment in the atom, it's also in there. How big is it? You see here, and these are the scattering factors at the neodymium L2 resonance. I'm just using neodymium as an example. Is 0.4 R0. So whereas the non-resonant charge scattering was 60, the resonance charge scattering was 7. The magnetic resonance scattering is 0.4, so less than 1% of the charge scattering. So it's a very weak effect. This is the scattering amplitude, and what you measure, these are complex quantities because the imaginary part of these things are responsible for absorption, and the real part are the typical dispersions that you get when you are at a resonance. So a Kramer's chronic transform of the imaginary part. So when you look at these effects, you don't see any magnetic field here. It's all electric field. So it's all related to an electric dipole interaction. And these two resonance scattering phenomena are a second order process where n is this intermediate state where you have this virtual electron that senses the valence electrons, and then it goes back, and this denominator is what gives you this resonant enhancement. Believe it or not, these numbers, although very small, they are much larger, orders of magnitude larger than the interaction of the magnetic field with the spin of the electron. So the first term here is a first order process which is responsible for absorption. So if you come in with X-rays and just excite an electron, that's your final state, and that's this first order process. So now that was one atom, and now we're interested in putting these atoms in crystals. And when you put atoms in crystals, you have crystallographic positions. There is symmetries that come into play, and the scattering from the different atoms either interfere constructively, destructively. You have to come up with what's called a structure factor. So you take these individual atom scattering amplitudes. Here I bundle the non-resonance and resonant charge with the resonant magnetic, with the different polarization factors. And you have this phase factor that sort of will tell you how the scattering from different positions in the lattice interferes with one another. And what we measure is, of course, a real quantity, not an imaginary or complex quantity. So we have to square this scattering amplitude. So remember, the scattering amplitude is proportional to R0, which is a length. The intensity is the cross-section is an area, which is the square of R0. And this is the intensity that you would measure in an experiment. So it's a square of this sum of terms. Now, we said that the resonant magnetic scattering is small, could be 0.1%, could be less, could be even 0.01%. So when you square such a small quantity, you get magnetic Bragg peaks that are much weaker than what you measure in neutrons, maybe 6 orders of magnitude or more. Now, when you're looking at antiferromagnets, where the magnetic periodicity is different than the lattice periodicity, you would think, okay, maybe I have some hope because the magnetic peaks will be separated in reciprocal space from the lattice peaks. And even though they are small, I can measure them. When I have a ferromagnet where the periodicity is the same as that of the lattice, the magnetic peaks are on top of the charge peaks, and there's no way you can measure 1 part per million easily. So
can you not dope the crystal with magnetic substances so the lattice spacing between the magnetic atoms be different from all the atoms?
I'm talking about general, antiferromagnets, ferromagnets. You can certainly do things to modify the magnetic structure and cause this commensurate thing to separate.
Yeah.
But if you have a material that is a ferromagnet and you want to study it, it becomes difficult with this technique. So now you say, well, this is a very weak scattering cross-section. How do you manage? And we manage because the synchrotrons, we produce very, very bright X-rays. And even if you lose millions and billions of photons, you still have a lot of photons left to measure the tiny cross-sections. And the synchrotrons have become brighter and brighter over the years. This is the sun, this is the light bulb, this is X-ray tubes in the lab. In a synchrotron, an electron is bent in a magnetic field, and when you bend an electron, you're accelerating it, and then you again generate dipole radiation. And when the electron is relativistic, the dipole radiation is very strongly focused in the forward direction. So as we go to next and next generations with more bright and brighter sources, we use these undulators where instead of bending the electrons only one, we bend them multiple times inside these alternating arrays of magnets. So these are undulators. So you start with a bunch of electrons, a lot of electrons in there, and you pass them through this array of magnets. So they wiggle back and forth. They are accelerated, and they emit radiation. And the radiation from each pass or from each pole interferes with the next one, and you get these constructive interference effects, which is an amplification that gives you a lot of photons. So the difference between the third generation and the fourth generation, the fourth generation is an upgrade that we just completed last year. So the APS at Argon is now a fourth generation source, oftentimes referred as diffraction limited sources. What they've done is take this electron bunch that was rather big. This is the dimension of the electron bunch before the upgrade, and this is after they squeezed this electron bunch and made this electron bunch much smaller. It's a factor of 100 smaller in the horizontal. It's not easy to focus electrons to such a, and so many of them into such a tight spot. This is about 10, 15 microns. That's the size of this electron beam. So when you focus this electron and you also reduce their divergence, this coherence amplification becomes larger and larger, and we gain another factor of 500 increase in brightness. With this last upgrade, it was a $850 million upgrade of the advanced photon source. This is a picture of the new accelerator, and this is new beamlines, and the whole accelerator complex was a new one. So how many photons we have? We have about 10 to the 13 photons per second in sub-micron beams. So we can take these X-rays and focus them into a very small spot, and there's a lot of photons. So even though our cross-sections are small, question?
Since your electrons come in bunches, your photon pulses also come
That's
in
right.
bunches.
Yeah.
How long are they?
That's a very good question. So yeah, so these electrons come in bunches, and they circulate. We have different ways to fill this accelerator, either 324 bunches or 48 bunches. So the spacing between them depends on the filling mode. The separation is between the pulses are either 11 nanoseconds or 75 nanoseconds. The length, the duration of the pulse, it depends on the longitudinal length of this bunch, and that's about 100 picosecond. Now, to wrap up this, some advantages of resonant X-ray scattering, because we are tuning the X-ray energy, and I forgot to mention that these undulators produce not very monochromatic X-rays. They are about 0.1% bandwidth of the energy. So if you have kilovolt X-rays, so it's a few hundred, or 10 kilovolts, it's maybe a few hundred eV. You can scan the gap between these magnetic arrays, so you control the magnitude of the magnetic field, and then the energy of these X-rays can be tunable. And then you use a monochromator, a crystal monochromator, to actually define the energy to a very high precision.
Did you say it was 13 photons per second?
13.
13, right there.
Yeah.
And only 10 or 100 picoseconds.
100 picosecond is the
duration of each pulse.
The duration of the
so
pulse.
In each pulse, you don't have a whole lot of photons.
No, of course not.
Okay.
I mean, but the beauty of this synchrotron or storage rings is that it's a continuous source.
Mm-hmm.
So you just accumulate. So we are, one turn is like microseconds, one pulse is picoseconds, but we are continuously putting photons and accumulating statistics. So right, if you want to do a single bunch, one measurement, one pulse measurement, it's very limited. So this resonance, you're tuning the X-ray energy to a particular atomic resonance. So this is an element-specific technique. If you have a material with many elements, you can pick up a signal from one particular element. The photoelectron lands in a particular orbital, so the technique is also orbital-specific, because the dipole selection rules dictate which L states couple. And it circumvents some of the limitations on neutrons because you can probe elements that are strong neutron absorbents like gadolinium or iridium. The beam brightness allows you to look at very small crystals, even, for example, in high pressure cells. And as we said, the source is a pulse source, so you can do time resolved studies, for example, pump probe studies down to 100 picosecond time resolution. So I want to give you an example of a topic that I will talk about tomorrow. So here is just a brief couple of slides to kind of pick your brain a little bit and highlight one example of where we use this technique. So this is in the Kitaev quantum spin liquid. What Kitaev proposed is that if you have a honeycomb lattice of spin half moments, and the moments are sort of like coupling, the components of the spins, the couple, are perpendicular to the bonds or the edges of these three edges of the honeycomb, X, Y, Z. You can see that if they are forced to be like that, the corner here will be frustrated because the spin at this position doesn't know if it wants to align perpendicular to X, perpendicular perpendicular to X, or perpendicular to Y, or perpendicular to Z. So which bond does it pick? So he showed, Kitaev, that this Hamiltonian, this exchange that looks like this, is like an Ising model, but the uniaxial anisotropy axis rotates from bond to bond. So it has a bond-dependent uniaxial anisotropy. He showed that this is an exactly solvable model that gives you a spin liquid that has excitations that are topologically protected. So there is this, probably his paper has tens of thousands of citations because people are excited about using this stuff for quantum computing. And the topological protection may allow you to get a quantum computing at higher temperatures, not at 10 millikelvin. So we are looking at these iridates because iridium has very strong spin-orbit coupling. And when you ask, how do I get my spins to align along a certain direction of the lattice or a bond, you want spin-orbit coupling. And for this particular system that has an iridium 4+ valence states, which is a low spin 5d5 electronic configuration, the wave function of this 5d state is such that if you have edge-share octahedra, it can be shown that the isotropic Heisenberg exchange, which is the typical way you couple spins in magnets, cancels out. It requires exactly 90 degrees super exchange interactions, and it has to do with having two different exchange pathways going on the top and the bottom. There is some quantum interference that cancels this isotropic exchange. This isotropic exchange only depends on the relative orientation of the spins. It doesn't care about the orientations relative to the lattice. So if this is cancelled and this guy survives, you can get Kitaev spin liquid in a real material that has edge-share octahedra with perfect 90-degree bonding. So this system has different polymorphs, two-dimensional, three-dimensional. They are called 2D honeycombs and stripy and hyper honeycombs, but all of them have this motif, which is these hexagons with the corners with the three bonds that could in principle host this predominant Kitaev interaction. But unfortunately, the angles in the structure are not 90 degrees, although they are edge-share octahedra, and the distances are not all the same. These are not regular octahedra, so this cancellation doesn't quite happen. And then you end up with magnetic order, but quite complex magnetic order, spiral magnetic order where the spins curl around, and that is because this Kitaev exchange is quite significant. And you see, if you look carefully here, you see some bonds where the spins kind of want to go perpendicular, but they really can't because the structural motif is not perfect. So the order in this incommensurate spiral phase, and this is the incommensurate wave vector, that means that the periodicity of this modulation is not the periodicity of the lattice. So the magnetic scattering from this order will be separated from the lattice or charge scattering. So we do these experiments. We have to square the scattering amplitude. We have the charge term and the magnetic term. And we want to do these experiments at high pressure, because what we want to do is we want to see if we can tune these angles and these distances to bring it into a more regular honeycomb lattice. And we have to work at resonance, and the iridium L3, which is a 2p3 half excitation, is 11 kilovolts. It's rather small energy for high pressure work, because the absorption of the diamond anvils in the high pressure cell is quite significant, as you see here. Typically you have 4 millimeters of diamond, and at 11 kilovolts, this is the transmission of 4 millimeters of diamond. You're down here. So what we do is we use diamonds that are laser drilled, partially perforated, to reduce the attenuation of the X-ray beam in the diamonds. And your crystal has to be thin enough, also about 25 microns, for the X-rays to go through the crystal. So here is just to show you that if you put your sample in a pressure cell and you scan your energy through the resonance, the iridium L3H resonance, you see this large enhancement, and the wave vector is 0.57. That's exactly the position of the magnetic order, of the spiral order. And if you move a little bit away from this wave vector, there is no magnetic scattering intensity. And if you go off resonance, the intensity becomes very small. So we can measure this. Rather, you see the signal to noise level is very nice. This is 10,000 times weaker than the Bragg peak nearby the 400 lattice or charge peak. So we can follow this under pressure, apply pressure. This is the 400 Bragg peak. As you compress the lattice, it moves to larger angles. And this is the magnetic Bragg peak, this incommensurate magnetic Bragg peak. You see that this incommensurate wave vector, which has to do with how the spins kind of lock to the lattice structure, changes with pressure. It becomes a little smaller, the peak shifts to the left, but then all of a sudden at 1.5 GPa, this peak disappears. And actually all magnetic peaks disappears, and magnetic order goes away. So, okay, you get very excited because you think, okay, maybe we are going into the Kitaev limit, and you have to come to a talk tomorrow to learn what really happens here. So by the way, this sounds pretty simple, but this was the first report of a resonant magnetic scattering experiments in a diamond anvil cell. It's not as easy as it seems. And when Libby here was part of this collaboration. Okay, how about ferromagnets? So you asked me about doping and how do we deal with this problem of separating what happens when the magnetic periodicity is the same as the lattice periodicity. Neutrons are great for that. How about X-rays? So you will say, look, the polarization dependence of this charge scattering and the magnetic scattering, they are different. So why don't I do polarization analysis and I try to resolve the polarization of the scatter beam to separate the charge from the magnetic? Well, it turns out that it's not easy because to do polarization analysis, what we do is we leverage the properties of dipole radiation. In dipole radiation, if you look at radiation that is polarized in a certain direction, you see the most intensity looking perpendicular to the polarization. But if you look along the polarization director, or in this case from here, you see nothing. There is no intensity there. So you need to add another crystal, a polarization analyzer, and diffract, because we don't have X-ray mirrors at high angles. We have to diffract from a crystal, and at 90 degrees, if you look at this, the charge scattering, let's say the polarization is out of plane, then it's not rotated. The magnetic scattering rotates the polarization, so it's pointing up. So if you scatter in the horizontal plane and you look directly perpendicular, you will see this guy, but the polarization from the charge scattering along this direction, you won't see it. But you need a 90-degree reflection to actually suppress this charge scattering, and it's almost impossible to find a crystal that will reflect, have a Bragg peak at 90 degrees at that resonant energy. So usually you get to 87, 85, 82, and the suppression factors, when you look at this term, are not large enough. You can maybe suppress a factor of a few hundred, but not a factor of 10,000 or more than you need. So that's a little bit of a problem. But remember what we've been doing, we've been adding these terms in quadrature. And we were saying, look, if you have magnetic and charge scattering, I have one amplitude, completely independent, I add the other one. But this is a complex quantity, and the question is, why don't we have interference term? When I square this, why don't I have this square plus this square plus the product and the complex conjugate of it? And that's actually what you have. But the trick here is that if you're using linear polarization and the photon in the scattered final state, they have orthogonal polarization states, there is no interference, because to have quantum interference or any interference, you have to have the photons in the same quantum state. They have the same energy. They show up in the same Q vector, the same point in reciprocal space, but they have different polarization here, so they don't interfere. One is horizontal, one is vertical. But if you use circular polarization, I will show you that there will be interference between the charge and the magnetic scattering, and we can leverage that for our advantage. And let me show you how that works. If you have circular light is nothing else than two orthogonal polarization states that are out of phase by 90 degrees, right? So the light rotates clockwise or anti-clockwise for the other helicity. So when you look at charge scattering doesn't rotate the polarization, so you go blue, blue, red, red. And you look at the magnetic scattering, it rotates the polarization, so blue goes from horizontal to vertical, and red goes from vertical to horizontal, but it's still circular or elliptical. So these two photons actually have polarization states that overlap. And then when I compute this scattering amplitude, now I have to worry about this interference term, because there is interference between the charge and magnetic scattering channels. So if I get that quantity, remember we call this 1, this is about 1%. I square this quantity, this is the direction of the magnetization, I get this term square, I bundle F0 and Fc and non-resonance and resonant charge into this Fe, I get this term square, and then I have the cross product plus the complex conjugate. And if I change the direction of the magnetization, this term, which is proportional to the direction of the magnetization, will change sign, but these two terms, they don't, because this is independent of magnetization. This one goes like the square of the magnetization. Now I take the difference between these two, and I end up with this term. These two cancel, and I end up with this charge magnetic interference. And this charge magnetic interference has information on the direction of the moment and on the magnitude of the moment through this magnetic scattering factor. And if I add these two for different direction of magnetization, then this term cancels, and I get this plus this, maybe divided by 2. And then we set the magnetic scattering. We know this term is 10 to minus 4 of this guy, so we can neglect it, and so we get the charge scattering. And then you can take the difference divided by the sign. We call that the flipping ratio, but the point is that this quantity now is large, because this was 1 and this is 0.01. Now I have a 1% quantity. The product is 1%. It's no longer 10 to minus 4. So again, 2 orders of magnitude. It's not a pure magnetic signal, but it's sensitive to the direction of magnitude of the magnetization. And the nice part is that reversing magnetization direction is equivalent to reversing the helicity of the circularly polarized X-rays. So I can do the same experiment by flipping the helicity and keeping the magnetization fixed. And here what I've done a little bit of algebra to convert these polarization vectors, unit vectors, into, Ki and Kf. It's just some geometry that is not super important at the moment, but it's very simple. You see that you're sensitive to the magnetization in the scattering plane, projections along Ki and Kf. Ki and Kf are the incident and scatter wave vectors.
If you go, the M is in the sample that is scattered.
That's right.
And how do you change the polarization of that?
No, well, I can change the magnetization with a magnetic field. I put the sample in a
So
magnet.
you apply a magnetic field on your scatterer.
On your scatterer,
scatterers.
yeah. Or you
Flip it.
switch the polarization of the X-ray beam and keep the magnetization fixed.
But X-ray beam is circularly polarized.
Well, the X-ray beam that comes from the synchrotron is linearly polarized, but we convert it to circular with a quarter wave plate.
All right.
And the quarter wave plates in X-rays is a whole lot different talk,
Okay.
because it's a very different ball game than the quarter wave plates they use in optics. But the main point here is the charge magnetic interference is not purely magnetic, but sensitive to the direction and the magnitude of the magnetization, only to the component in the scattering plane. And now I have a 1% signal instead of 1 part in 10,000. So I want to show you one example about permanent magnets where we use this charge magnetic interference. And little we knew 20 years ago when this work was done that permanent magnets will become such a large commodity and be central to the trade war between the US and China. It looks like they are as valuable as the most advanced NVIDIA chips. So to get a good permanent magnet, you want the best of these two worlds. You want very large magnetization and you want very high coercivity so that the hysteresis loop is square, a big square, and tall. So the magnetic energy that is stored in this magnet is the area in these hysteresis loops. So this is how permanent magnets have evolved over the last 5,000 years. This is a lodestone, which is kind of magnetite, naturally occurring in iron ores. This is ferrites, and this is neodymium iron boron, which is the strongest magnet that we can produce today. And how do you make this hysteresis look like this? You put a lot of iron. All the orange here is iron to get a large magnetization. There's a lot of iron atoms. And then you need an isotropy or coercivity. You use rare earths because rare earths have an isotropic 4f orbitals. And when you put them in the lattice and in a crystal field, you deform the charge density, so the wave function is anisotropic, and if you add spin-orbit coupling, you can couple the direction of the spin to the crystalline axis. So these neodymium iron boron magnets have a c-axis anisotropy that is dominated by the neodymium ions. Now, when you look at this structure, the ordering temperature is high, makes it a good magnet for even for high temperature applications. Now, there's a lot of atoms in the unit cell, and most of it is iron. So if you have a magnetometry measurement or even a neutron measurements, you will see the signal mostly from iron. So we are interested in the neodymium in particular because that's what's giving this magnet its magnetic hardness or the coercivity. It makes it hard to demagnetize. So it's a small neodymium moment compared to the large, or magnetization compared to the large magnetization for iron. So our techniques are perfect because we can tune the X-ray energy to a neodymium resonance, separate the neodymium from the iron. But we need more than that here because there are two neodymium sites that are crystallographically inequivalent. So if you look at this, I made a plot where the neodymium G site is at the center here. You see this site has 1 boron atom and 3 neodymium neighbors. The other neodymium type of atom, the F site, has 2 borons and 2 irons. 2 borons and 2 neodymium atoms. So they have different neighbors. That means the crystal fields are different. And you would expect that perhaps each one of these neodymiums will contribute differently to the magnetocrystalline anisotropy or the coercivity of this material. So we want to separate not just the elements, but we want to separate also the sites. So how do we do that? So we go back to the very simple structure factor where the atoms are in a particular arrangement, so in the symmetry of the lattice, and they have different structure factors. So when you look at the contributions at a particular Bragg condition from the one type of neodymium or the other, in this case is the 110, 220, 440 Bragg peaks. It turns out that the 110, mostly one neodymium site, the G site contributes. If you go to a 220 Bragg peak, the structure factor or the interference between the 4 neodymium atoms there are 4 of each. They interfere when they scatter, flips. Now at 2, 2, 0, the F sides are dominant, and at 4, 4, 0, they are equal. So in a simple picture, at a particular Bragg condition, you can have constructive interference for the blue atoms where the scatter waves interfere constructively, so you have a strong Bragg peak from these atoms, but at the same time, the diffraction from the other sublattice vanishes or goes very weak. So it's basically just Bragg condition. So this is a ferromagnet, so the magnetic scattering will be on top of the charge scattering. So in an experiment, we can put the sample in a magnet. Back to your question, put the sample in a magnet, so we can flip the direction of the magnetic field if you want to do a hysteresis loops or something. We have the undulator. We can tune the gap to change the energy. We can scan the angle of the monochromator to pick, and as we scan through a resonance, we have this phase retarder or quarter wave plate to convert the light from linear to circular, and we can flip the helicity with this phase plate. And we can measure this charge magnetic interference scattering, and especially the ratio of the difference divided by the sum by flipping this helicity and calculating this quantity. So what's shown here is in blue is the resonance charge. So we are adding the 2 helicities back here. We are adding the 2 helicities, and remember the other terms cancel. We just get the charge scattering. So the blue is the sum of the helicities. So that's your resonance as you go through the neodymium L, I think 2 edge. For different Bragg conditions. So in this condition, one neodymium side contributes, here is the other, and here is both. And the red is the difference in the Bragg intensity for left and right helicities. So you see this is about 1%. This is the gain we got in this 1% charge magnetic interference. So this red signal is sensitive to only one type of neodymium atom, here, the other one, or both. And one interesting point here is that if you look at this geometric factor that has sensitivity to the direction of the magnetization, you can immediately see that if you reverse the magnetization, it changes sign. And if you are at small Bragg angles where cosine 2 theta is not very large, or 2 theta is not large, cosine 2 theta is close to 1, Ki plus Kf is parallel to the magnetization and the applied magnetic field. So in a way, what you're measuring is the projection of the magnetic moment along the field. This is the same that you measure in squid magnetometry. It's just that you have element and site selectivity. So what we can do here now is say, okay, let's tune the energy to this square, this particular resonance when the red charge magnetic interference is the strongest. And now let's reverse the magnetic field. And I can do a hysteresis loop that is only sensitive to neodymium and only sensitive to one or the other side. And these are the curves here. For the 110 Bragg peak and the 220 Bragg peak, I stay at this energy, I flip the direction of the magnetization, and you see that the hysteresis looks like quite different. One is nice and fat and square, indicating that the G sides have strong anisotropy. It takes a large field to flip it. But the other one kind of flips at very low fields. And in the bottom panel, what we show is the mathematical average of these two curves, F flat G over 2. The data collected at the 440 reflection, which is an equal contribution from both sides, and also the XMCD signal, and XMCD I'll talk about in a minute, is an average of the two contributions. It's an absorption probe that has no Q dependence, so it averages the two neodymium sides. So this is, of course, very important because it tells you that in this structure, only one type of neodymium sides is contributing the most to the magnetocrystalline anisotropy. So if you can figure out how to replace the other side and put a different type of rare earth there, or do some other trick, even put in a gadolinium atom that is isotropic and it doesn't kind of compete with the other anisotropy, maybe you can get a better magnet.
Does this result concur with the bulk measurement of a neodymium magnet that you said is very strong? Because the numbers here don't look too big.
Oh, right.
1,000
Right. So this is a single crystal.
Uh-huh.
So this is a very pure, out of the oven single crystal,
Ah.
which is by and large kind of like monodomain. So it doesn't have pinning centers.
I
It doesn't
see.
have
I see.
defects. It doesn't have
I see.
ways
Thank
to lock. So
Uh-huh.
in single crystal, the coercivity naturally is smaller. And yes, it agrees with the magnetometry in the sense that although the magnetometry is dominated by iron,
Yeah.
you will see low coercivity in a single crystal. How about absorption? Everything I showed you so far was scattering. A photon comes in, a photon comes out, and this is the resonant magnetic scattering. We talk about this second order process, this intermediate state. We talk about separating in antiferromagnets, you get pure magnetic scattering separated from the charge. We talk about charge magnetic interference. But how about absorption? Absorption, we said, is related to the imaginary part of these complex scattering factors or scattering amplitudes. And absorption is a first order process. You come in, you excite an electron, and you become sensitive to the spin polarization of the valence band or the valence orbital. And this technique is much more simple. So what we call it magnetic absorption. It's magnetic dichroism, and it turns out that if you use circular light, and if you use circular light and you measure the difference in absorption for left and right helicities, which is the X-ray magnetic circular dichroism, it's the most sensitive to the spin in the atom. So I want to say a little bit about X-ray magnetic circular dichroism. Circularly polarized photons, they have a spin of plus minus 1. It's helicity. So when you come in with a circularly polarized photon and you excite a photoelectron, the spin of the photon has to be conserved. So you sort of transfer that angular momentum to the angular momentum of the excited photoelectron. So the colors here are showing that if you come in with right circularly polarized X-rays, you excite, you see 75% spin down and 25% is spin up. So you excite mostly one color of spin. And if you reverse the helicity, the red, you see 75% here, you excite the other color of spin. So you have spin polarized photoelectrons, they go into an empty valence state, and if you take a difference between these two measurements, you become sensitive to the spin polarization of the valence band. So if the valence band, it has different density of states, or empty states, for spin up and spin down, you can sense that with this technique. And you also see something interesting, that if you go from L2, which is an L minus S to P1/2, to the other pair in the spin orbit split to P states, which is L plus S, which is 3/2, you see that RCP, blue, excites spin up here, mostly 75%. The other edge is spin up instead of spin down. So because the spin orbit coupling in these core levels has a different opposite sign. So you produce opposite signs of polarization. So this will become important when I show you some rules that you can use X-ray absorption across these two these two core levels to actually get information on orbital magnetization. So the measurement is very simple. You measure the absorption for one helicity, the other, and you can take the difference to remove the magnetic part from just the simple X-ray absorption, which is the charge part, and the spin average empty density of states. And this is, again, element and orbital specific, and it's a vectorial probe because it measures the projection of the magnetization, which is the quantization axis, along the X-ray helicity. So if you magnetize the sample perpendicular to the X-ray helicity, you see nothing. So you have to magnetize the sample with a projection of the moment along the X-ray helicity. And this is very related to magneto-optical Faraday and Kerr effects. Basically, it's the X-ray version of those magneto-optical effects. So I want to spend a second here because this is important. Most magnetometry techniques measure the total magnetic moment, which is spin and orbital components. But XMCD can actually separate the spin and the orbital components of a magnetic moment. And if you see look at these numbers, see that the spin polarization of the excited electrons is not 100%, it's actually 75%. And because the missing part is actually orbital polarization. When you excite this core level in this spin-orbit split core level, it mixes spin and orbital components, and the photoelectron carries spin polarization mostly, but also orbital polarization. So if you measure XMCD across these two edges, as shown here, the areas of A and B can be used to actually calculate separately the spin and the orbital components. So you can see here, if A is equal minus B, so L3 and L2 edges, if the areas are equal and opposite, the orbital moment is 0. But if they are different, the orbital moment is not 0.
And XMCD means X-ray magnetic charge difference?
X-ray magnetic circular dichroism.
Oh, I see. Thank you.
So here is an example. If you have a metal and you put a little bit of iridium in the alloy, you have a metal with a very broad 3D, 5D band. The orbital moment is quenched. And you see that the XMCD at the L3 and the L2 are more or less, they have opposite signs and they have more or less similar areas. And the orbital magnetization is very small, is 1% of the spin moment. If you have, for example, an iridate that has very strong spin-orbit coupling, but now it's not a dopant, but it's actually a band material where the 5D band is split by spin-orbit coupling, and the orbital moment is not quenched. You see that the XMCD at the L3 and the L2 edges, not only they don't have the opposite signs, but one is very large, the other is very small. And that already tells you that there is a very large orbital moment in this iridium 5D wave function. And you can actually quantify it, and in this case, it's the orbital angular momentum is almost 3 times larger than the spin angular momentum for this particular iridium 5D 5 configuration in the presence of spin-orbit coupling. So this is a very important feature of XMCD because, as you know, spin-orbit coupling is at the very root of many, many modern effects in topological materials. So you have spin momentum lock-in, you have band gap openings in the Dirac cones, you have spin transfer torque, Kita-ev exchange anisotropy, all of that has to do with spin-orbit coupling. So the ability to separate the orbital magnetization from the spin magnetization is quite a plus.
And you're doing it on the atoms of iridium?
Yes, we are resonating. You can do it on any atom, but so you can do it on iron, you can do it on cobalt, you can do it on iridium, you can do it on any suitable resonance.
I see.
Yeah.
With large spin-orbit coupling.
Well, you want to find out, is spin-orbit coupling active and present? And then you go, okay, I'm going to measure this XMCD at these 2 spin-orbit split edges, and I can apply the sum rules. The one limitation is that this is for 3D, 4D, 5D systems. Okay. Yeah. So first, second, and third row. For rare earths and other elements, the sum rules become very complicated, and it's not so easy to separate. So just to summarize the XMCD, again, is element and orbital specific, but one limitation is that it requires net magnetization over the probe sample volume, because you need these bands to be spin polarized. So it's very different than the resonant magnetic scattering. You can probe antiferromagnets when you have no net magnetization, and you pick the magnetic Bragg peaks. Here you need net magnetization. You can separate spin and orbital moment, which is very difficult to do otherwise. There is no Q information, so we can never do the neodymium site-specific thing with this technique, because it will measure the contribution from neodymium, but it cannot separate size based on symmetry, because there is no Q information. It's a Q equals 0 technique. You can use it in ferro-ferri magnets. In ferri magnets, you have two sublattices with different magnetization. So again, it's element specific. If you have a paramagnet and you apply a magnetic field, you orient the moments and you induce magnetization, you can use it. If you have an antiferromagnet that is canted, either in magnetic field or naturally, like in a weak ferromagnet due to, say, the Shalansky-Maria interactions, then you can also use it. And the most important thing is that it's insensitive to magnetic background. So that's a great advantage over conventional magnetometry, because if you have very small magnetic response in a huge background from, say, a monolayer sample on a thick substrate or a tiny sample in a pressure cell that has a magnetic response, so it's even demonstrated that you can measure a single atom response by coupling X-rays with a scanning transmission microscope. So I don't know, I still have one more example, but it seems that we are out of time, and probably want to leave time for questions, so maybe I should stop here, and because I'm supposed to stop now, right? Yeah. How much time? This will take probably 5 minutes, but then 7 minutes, and then we want to have questions. And
that sounds good.
Huh?
That sounds good.
So stop?
5 more minutes, I think.
Oh, continue?
If you need 5 more minutes, I'm okay.
Okay, or stop? Vote, or? Okay, well, maybe just very quickly, I'll go very briefly. This is another example where everything comes together. This is where we use XMCD and resonant magnetic scattering, and you need both techniques to actually understand what's going on. It's the 214 system. I think everybody's familiar with the cuprates, the parent compounds of the high TC superconductors. This is an analog based on iridium. They have both this G-type antiferromagnetic structure, although this one has rotation, so you see the spins are rotated due to the Shalansky-Maria interaction. But incredibly enough, these two, although this guy has a very big spin-orbit coupling in the iridium 5D moments, the magnetic excitations are almost identical. So there's some differences. You see this goes down a little bit, this doesn't, but very much the same magnetic excitations. And people believe that magnetic excitations are very much related to high TC superconductivity in cuprates, like spin fluctuations and excitations. So, so despite this having a strong orbital spin-orbit coupling and orbital magnetization, the Hamiltonian is pretty isotropic. There doesn't seem to be much anisotropy. Now, they are also analogs because the cuprates have one hole in an EG electron. It's a copper 3d9, which is Young-Teller active, and there is one hole in the x squared minus y squared orbital. The iridates in the 4 plus 5d5 low spin configuration, when you turn off spin-orbit coupling, you have one hole in these so-called J half states. It's a J effective half state, which is T2G electrons instead of EG electrons. But it's one hole physics in a half field band that makes correlations very important. So like Mott correlations, and you get either Mott insulators or charge transfer insulators. But there is a lot of interest in understanding these parent compounds because superconductivity emerges when you dope them. At least in this one, nobody succeeded in making superconductors by doping strontium-2 iridium-04 yet. But there is a belief that spin fluctuations may be related to superconductivity, like in resonating valence band model of Anderson and such. So the interesting part about this system is that, you see the octahedra rotated, around the z-axis, and these rotations cause the spin moments to also rotate together with the octahedra due to spin-orbit coupling. And this stacking of this net moment, every layer has a net moment pointing to the right, to the left, to the left, to the right. So that's how the little moments are stuck along the z-axis, but it's an antiferromagnetic structure. So at zero field, if you apply no field, everything cancels. It's an antiferromagnet with no net moment. You cannot do XMCD. You can only do resonant magnetic scattering. But if you apply a very small field, the exchange coupling across the layers is extremely weak, micro EV energy range. So a very small field of 0.2 Tesla or so causes the layers to rearrange so that the little canted moment, now they are aligned and you get a net moment. It's very small, but you can measure it with XMCD, and then you can use some rules to separate the spin and orbital moment. And here we see again that if you look at the L3 and the L2 edges, you see this is very large, this is very small. Look at the scale, this is 3% XMCD on the blue. At the L2 is like 0.3%. So a factor of 10. That means there is a large orbital moment, and in fact the orbital magnetic moment is larger than actually equal to the spin moment, which is 2 times s. So the wave function of these iridium atoms is very complex because the spin and the orbits are coupled, and you actually get something like this, which we don't have time to talk about. But what we did is we put the sample in a pressure cell, and we say, okay, I can apply a magnetic field, induce a little bit of a moment, and then I can measure XMCD. And when I go to, this is the hysteresis loop, and when you get to about 20 GPa, that hysteresis loop collapses. There is no magnetic response. So this ferromagnetic, canted antiferromagnetic order went away. It's no longer there. We don't see a magnetic response. And you say, well, look, XMCD is only sensitive to the net magnetization. But that's this little canted moment because of the octahedral rotation. What if the octahedra are no longer rotated? What if pressure removes this rotation, and now you have a perfect antiferromagnet with no net moment? Is a G-type antiferromagnet. So you want to measure magnetic scattering, resonant magnetic scattering. And the interesting thing here is that this is the zero field canted moments as you go through the layers, left, right, left. And if you apply a magnetic field, you get this. And because you have these different periodicities of these arrangements, the magnetic Bragg peaks have different selection rules or different symmetries that come into play. And you see that there are magnetic peaks in zero field. The orange is 1-0 even peaks, and when you apply a magnetic field, it's 1-0 odd peaks. And we are looking at the antiferromagnet in zero field. This one. I'm not going to apply a magnetic field, so I'm supposed to see 1-0 even peaks. So here is the experiment. These are 17, 18 is the L index, and then 5, 6, 5, 6. When we go to low pressure, we don't see the odd peaks, we only see the even peaks, and we expect from these stacking of moments. But then as I go up in pressure, it switches. All of a sudden, I see the odd peak and not the even peak. And if I go to higher pressures, they become equal. So this is what happens. It's a crossover from this type of magnetic stacking of these ferromagnetic moments along the z-axis. It goes from here to here without applying a magnetic field, just by squeezing the thing. That's quite interesting. That's because you're changing the exchange interactions between these layers. And if you keep going and you go to the 20 GPa, remember the hysteresis loop collapses. Here the magnetic signal also disappears. So we no longer see it goes here, it switches, and then there's something weak, and then it goes away. So both XMCD sees that the magnetization goes away. Resonant magnetic scattering sees that the magnetization goes away. There is no magnetic order. We look for other magnetic peaks. We don't see any. So we can build a pressure temperature field diagram, and as a function of temperature at zero pressure, it goes paramagnetic at 200 and something Kelvin, and as a function of pressure at around 20 GPa, it goes paramagnetic. And this is a second order transition that you can scale it, and you can find an order parameter. It looks like it becomes a paramagnet at low temperature. So if you go at low temperature, which is the experiments we did, the magnetic order goes away, becomes a paramagnet, and you can measure the temperature dependence of this. There is no magnetic order, but there is strong correlations between the spins. This magenta curve is what would you expect from the susceptibility if it was just a Curie paramagnet with no correlations between spins. This is what we measure, and even at 1.6 Kelvin there is no ordering, so very strong frustration and a linear dependence of the magnetization at 25 GPa, and it also remains an insulator. So this is a resistivity measure at high pressure. It remains an insulator, and there is no lattice anomalies. If you do diffraction, You see no changes, no discontinuities in lattice parameters, no structural phase transition. So it looks like an order-disorder transition that may be something speed liquid-like. So how do you get magnetic frustration in a square lattice? Because you're looking at 5D orbitals, which are very extended. The radial extent of, spatial extent of these wave functions are very large. You may have higher order exchange couplings that may lead to frustration, and there is thousands and thousands of papers of how do you get a spin liquid in a square lattice. Whether we have it or not, it's not clear, and the main challenge is that there is almost no technique that can probe magnetic excitations at high pressure, especially at 20 GPa or higher. So inelastic neutron scattering is very, very bad because of the collimation to look at very high pressures. And other techniques are also very hard to do in the pressure cell. So you have to look at magnetic excitations to see if the excitations are trivial, like magnons, or if it's spin liquid like excitations like spinons, which are fractionalized excitations that are much more complex. We don't have the ability to do that, so this is something for everybody in this community to think about. And the neutron community is very interested in doing this. Their second target station upgrade at Oak Ridge is trying to get very small neutron beams to do high pressure experiments and to perhaps do inelastic neutron scattering to look at magnetic excitation. So this is my final slide, takeaways. Resonant techniques can probe magnetism with element and orbital specificity. These are ideal to isolate contributions, magnetic contributions in the presence of very large magnetic backgrounds. Small sample volumes in pressure cells, thin films, monolayers, and thick substrates, multi-component systems, and also magnetism carried by valence electrons that are not the primary electrons. For example, in rare earths, most of the magnetism is in 4f electrons. But the 5D electrons are super important because they mediate the indirect exchange, usually referred to as RKKY interactions. So you can probe the polarization of the 5D states as they breach these magnetic interactions. It bypasses the limitations of neutron scattering in some aspects for strong neutron absorbers, we talk about small samples. And again, there's some rules when you measure XMCD across spin-orbit split edges. Separate spin and orbital moment, which is very important for understanding non-trivial band structures, topological materials, and so forth. And the extreme brightness of synchrotron sources, especially the 4th generation sources, circumvent the small cross sections that are involved. I encourage you to look at the APS website if you're interested in becoming users. It's an open user facility. Everybody can apply. Everybody can come, and we are there to help. So. Thank you, and sorry it took longer than I was supposed to.